So welcome to today's webinar. This is the Coreform Cubit Advanced webinar. I am Matt Cederberg, the CEO of Coreform, and I'm joined today by Randy Morris, the Director of Sales at Coreform, and our guest, Kurtis Ford from Sandia National Labs. The agenda today, I'll just briefly introduce Coreform, and then we'll jump into the master class, and Kurtis will talk about how to use Cubit to hex mesh an evolving level set for a coupled fluid mechanical simulation. So some background on Coreform. So we're the fastest growing CAE company on the Inc. 5000 list in 2020. We were established in 2016, and we acquired CSIMsoft in 2019, and along with that acquired the Trellis product line, which was the commercial version of the Sandia National Labs Cubit software. And we rebranded that as Coreform Cubit, and are making significant investments in that software, continuing to develop it jointly with Sandia National Labs. We're based in Utah, but since COVID hit, we've gone fully remote, and I think all of our hiring since COVID has been outside of Utah, spread across the US and Europe. So our product line at Coreform, our focus is on allowing you to make safer products faster through better math. So again, we have Coreform Cubit, which is the focus of today's webinar, which is written for advanced meshing for challenging simulations. We also just released Coreform IGA, which is an isogeometric analysis solver for nonlinear structural response. So this is what we're really excited about. We're going to be having our first webinar introducing this product in February. So you can go to coreform.com and sign up for that webinar. One of the reasons that we are doing this series promoting Coreform Cubit is that we now have a free non-commercial use license of Coreform Cubit available called Coreform Cubit Learn. You can also get directly on our website as well. So the learning objectives for today's webinar are to, one, help you understand how Cubit can be used to prepare meshes for advanced simulations. This follows up on a basics webinar that we gave just before the break that Randy Morris gave, and that's available as a recording on our website. But one of the reasons that we grabbed Kurtis for this is that we've known Kurtis for a while, and we're impressed with how expertly he uses Cubit. But it's been interesting for me to notice how, as an advanced analyst, he's able to create advanced workflows in Cubit that even beginners can follow. So that's the goal of this webinar, is that regardless of your level of experience with Cubit, whether you have used it a lot or a little, that you should be able to follow what Kurtis is doing, and that should be able to enhance your work. So with that, I want to take a poll to help inform Kurtis as far as kind of what the experience level is on the call today. I'm just going to launch this poll. And if you wouldn't mind just taking a second to fill this in, help us understand how much experience you have with Cubit. If you've never used it, if you've tried it but haven't succeeded yet, if you've successfully used it on a few projects, successfully used it on many projects, or if it's critical software that you use regularly. I'll just go ahead and leave this poll open for just a few more seconds to help us get some understanding of who's in the audience today. Let's go ahead and close this in 5 seconds. Okay, so here's the poll results. Just for everyone's benefit. So got about a quarter of you that have never used Cubit before. Nearly half that have successfully used in a few projects, about a quarter that have critically used this every day, and then a few of the other responses as well. So hopefully with that background, each person will get something out of this webinar today. So I'll just introduce Kurtis. So Kurtis Ford is a solid mechanics analyst from Sandia National Laboratories who received both his bachelor's and master's degree in mechanical engineering from the University of Utah, the last one in 2011. His research interests have included the imperfection sensitivity of buckling, highly flexible beams, fracture and thin coatings, mechanical modeling of welds additive manufacturing, Weibull analysis on complex stress fields, coupled with multi-physics modeling, digital twins, smart materials, and nonlinear viscoelasticity of epoxy thermosets in inorganic glass. So throughout the webinar, as you have questions, both Randy and I will be here. If you ask us either via QA or via chat, please feel free to do that at any time. I know Kurtis is planning on taking about a half hour for his remarks, so there'll leave plenty of times for questions at the end, or if we see a question come in that warrants an interruption, we're happy to do that as well. So with that, I'll turn the time over to Kurtis.
Thank you, Matt. So I'm going to go ahead and share my screen. So I'm excited to talk to you. So like Matt mentioned, hold on, let me see if I can get this to. So I was going to start and introduce myself very briefly, and then I'll show you guys very generally how I use Cubit. And after we do that, I'll introduce the model I'm going to talk about, which is an additive manufacturing model, and then we'll jump into the Cubit demo. And I'm going to try and reiterate over and over exactly how the workflow works so that it's memorable. So like Matt said, I have several research interests, but my job role at Sandia is I work in a consulting group, and most of my expertise centers in physics, not numerical methods, although I do have some experience doing research on that front. Over the course of all of these research topics I've looked at, I have used many different FEA codes, and Cubit is my favorite mesher. And it really is the only mesher I've used for several years. And the reason for that is I like the intimacy with CAD that they offer. And then more importantly, the real biggest reason I keep coming back is the user experience and mainly the journaling. So Cubit's journaling is exceptionally intuitive in my opinion, and it's versatile, so you can use it in a lot of different ways. For example, you can automate things with an internal template tool called Apri Pro, or you can use Python, and I also use a lot of Bash. So this is something that's very valuable in my workflows and powerful. So that's the number one reason I use a Cubit. So typically when I open up a new model in Cubit, what I'll do is I'll open it up in the GUI and I will click around a whole bunch and figure out exactly how to mesh it. And then down here in this window, all the commands are listed, and I'll save those commands and create a journal file. And once I have that journal file, I don't open the GUI anymore. I just take that journal file and I automate the process, and then I can modify it for different studies. And that's how I'd encourage most of you to work. You figure out what you want to do with this GUI, and once you have it, you should use these journal files. So the model I'm going to talk about today is a model I used for an additive manufacturing process. This has actually recently been accepted to the Journal of Computational Mechanics. You should see it next month. The motivation for the model is we wanted to have a coupled fluid solid mechanics model. So the reason we do that is easy to see with this example for additive glass. So this is a project I worked on with Missouri SMT, and I'm now working on a little bit with Notre Dame. But what you see is you have this glass rod that's fed into a laser, and it melts it just a little bit, just enough to change the shape, but it doesn't become a fluid. It doesn't have a low viscosity. So what you see on a final structure, you can see that you have this morphology that really depends on the temperature, where it was like a fluid and like a solid both. And so to be able to model this successfully, we need the fluid mechanics in order to get this shape right. But then we also need the solid mechanics to predict the residual stress. So for this particular structure I'm showing, this is the residual stress that an intern of mine named Brett Kurtis measured. And we want to be able to predict that. And in order to do that, we need this coupled model. And it turns out that really to get these morphologies, it's actually useful for the metal too. So glass, it's a little more obvious, but in the metal, when you're on the mesoscale, you'll find that including the fluid mechanics will show a difference in your morphology and your temperature history. So the way the model would work, I'm gonna skip this slide, is we run a fluid mechanics model, and from that we would get a temperature history and a morphology. And then we would take that morphology and that temperature history and use it to run a solid mechanics calculation on a Lagrange mesh. And that would give us a residual stress, which is what I'm showing in this picture, and then also material properties, depending on what kind of material model you use. Now, the thing about doing a model like this is the meshing is extremely challenging. And the reason for that is the type of considerations that you would use for a fluid model are not the same that you would use for a Lagrange solid mechanics model. So let me show you, go back and show you this example. So here is a fluid model of a weld. And I'm actually going to do a weld for the demo today, not glass, because it is a little more interesting. But what you see is we put this hot spot in, and then the metal changes shape. And it's not shown here, but we actually have a mesh in the air because we are taking into account vaporization and all these other effects that matters for the air. But the solid domain for the metal is changing in real time. So if you look at the mesh of this simulation, so here's the mesh. So initially the mesh is metal and air. The red is the metal. But as it heats up and some of it vaporizes and then it turns into liquid and starts to splash, you'll notice that the metal is changing shape. And the way that we resolve this in our fluid model is using a tool called CDFEM, where you have this initial TET mesh, and then you splice those TETs along the level set that represents the metal in order to resolve the temperature gradients at that interface. So you'll see that all right here on this boundary, all these TET meshes are getting split. This is really cool for a metal or for a fluid model, and it's very powerful. But the problem is these meshes, you really can't use them for a solid mechanics calculation. They don't have, even in cases where you're able to use a TET, these meshes are just too low of quality. So that's where we use Cubit. So the TET mesh is generated in Cubit here, and then the CDFEM is done in our solver. So here's how I would do the solid mechanics mesh in Cubit. I would read in that TET mesh, and each of these shape changes I'm showing here represent a new mesh. And so in my solver, I can actually output, this particular shape, and then the next shape, which is this one, and so forth, and get a whole list of meshes. Okay, and then I would read one of those meshes in to Cubit, and you see you have an air mesh that's in gray, and then the red is your metal. So in Cubit, I would delete the air because I'm not going to use that for my Lagrange calculation, and I'd be left with this TET mesh. Now, in this example I'm showing on this slide, the TETs are a little higher quality, but they're still not good enough to do a reliable Lagrange calculation. So I will delete these TETs and I'll be left with a mesh-based geometry. And at this point, I can either export that as an STL file, or I can just directly mesh it in Cubit, and that's what I'll do today. And the tool that I'll use is Sculpt. And here's an example of a mesh generated by Sculpt. And the way Sculpt works is you essentially immerse a grid and then you modify it and smooth it to fit the outer boundary. And so it works really well for things like this where the shape is nearly arbitrary. Now, once I have done this, what I would do is I would take the journal commands, like I told you, and I would put them in a script, and then I would run this script on every single iteration of the CDFEM. And so your final state should be a model that looks like this. So if this is your fluid model here running on the bottom left, then you'll have a hex mesh for each individual shape. And so then we can have a Lagrange calculation for every iteration of our CDFEM. And all we have to do is, well, it's not trivial, but we have to track our state variables and map our temperatures across each of those meshes. And we're able to do that. Now, one other thing that you may want to do, in this example, you see that the mesh is very uniform. And in some cases, you want something more complex. So in the case of additive manufacturing, a lot of times we want a real fine mesh near the hot spot, but not so much away from it. So what I can do in Cubit is I can make a custom mesh, and that's the mesh that you immersed, and then Sculpt forms it. So in this picture, I'm showing you the mesh that will be immersed right here on the left. And then right here is the geometry generated from CDFEM that will sculpt this. So here is the mesh that I generated using that. So you can see I have adaptivity incorporated into that sculpt mesh where it's coarse on the outside and then it's fine in the middle. Now I would recommend if you do something like this, this is a little more complicated. And when I did it, I had to work with Cubit developers to make it work. And even then, it's kind of temperamental. You can see, for example, right here, they're is some mesh quality issues and things that I had to deal with when running this. So I'm going to go ahead and start my demo. And what you should expect to see is I'm going to generate a mesh-based geometry from those TET elements. I'm going to create an STL file. Then I'm going to mesh the STL file with hexes. And then I'll use those journal commands to make a script that can be fully automated inside of Cubit using April Pro. And then I'll run the script in batch mode. And then if we have time, I'll show you how to add that mesh refinement. So let's jump over to Cubit. So like I said, I always start with the GUI like this, okay? Because it's way easier to see what you're doing the first time through. Even after you have the commands memorized, it's a lot easier to just see, you know, kind of see how the geometry works. So here is my list of TET meshes. So generally in one of these models, I'll have hundreds or more TET meshes, but we're just going to look at one. So I put 10 in here so I can show you how to do multiple, but for the first one, we just pick one. We'll say 239. And I'm going to choose this option because I want a mesh-based geometry. It runs a little slow. I actually picked a relatively small model, but it's still kind of slow at first. And this is why later we'll automate it. Another reason to do that. So once it comes in, I'm going to type quality. I'm going to show you the quality metric of these TETs. So you can see why it would be such a challenge to do a Lagrange calculation on it, even if you did some of the stress averaging that you can do in TETs to eliminate locking. I wonder why I can't see it. Oh, okay, it got lost. So this little button helps you when you're lost. So the yellow is the error. So I'm just going to go ahead and delete that. And then this is the solid material. Now some of this is melted, but we still want to mesh it. So if I do quality hex all draw mesh. Oh, that's not the right syntax here. Let me double check that real quick. See, so I keep a list of some of the quality hexol draw mesh. Well, maybe that's not going to work either. Okay, so I had to do vol since it's a mesh-based geometry. Anyway, so you can see that the quality is pretty decent down here, but right where that CDFEM was going on, it's not so good because it's red. And when I look at quality, really the best metric for me, especially for a Lagrange calculation, is scaled Jacobian. And you can just type scaled Jacobian at the end of this. And this is telling you what your Jacobian is. And if your Jacobian is near 0, what that means is your elements are on verge of inverting. And that's no good. So you can see this is very close to 0. So that means any kind of strain that deformed those nodes, and it would probably invert and you couldn't run it. One thing that's handy to do when you're looking at your mesh quality is to use this button. So you can do a cross section and you can see, you know, these TETs up here at the surface where CDFEM was working its magic are also too poor to use for a Lagrange calculation. So I need to move that so I can. Matt, do you know how to move that toolbar? There we go. So draw vol all, so I can get back to where I was, and then I'm going to right click it and I'm going to delete the mesh. So now I just have a geometry, and you can actually export this from Cubit as an STL file. But we don't need to do that. So one thing that you'll notice is because it's a mesh-based geometry, you can't cut it. So for example, if I come down here to volumes and I pick these scissors and say I try to cut it on the YZ plane. So normally if I had drawn something in a CAD tool or here, I would be able to make this cut. But when I do it now, because it's mesh-based geometry, it won't work. I'll get this error. And even if I enable dev commands, it still won't work. Don't try it because it'll just run really slow and then crash Cubit. So now that I've got my geometry, all I have to do is run the Sculpt algorithm. So I click over here on the mesh icon, and I'll pick this volume, which is volume 3. And notice by default, Cubit will actually have this unselected. If you're meshing something, you should use advanced settings. I don't care if you only use Cubit for a day. These are really handy. You should look through these and click through them and see what they do. So for example, one that's really useful for this are these sizing commands. So here I can tell exactly what size I want it, or I can use this auto tool, which I find to be pretty handy. And you come down here and you can hit preview, and it will show you roughly what your element size is going to be. So this is pretty handy. So watch what happens if I scale it down. You can see that now your mesh is way finer. See how much littler it is? But it takes a lot longer to run those. Another thing is you have this parallel command. So if you're running on HPC, you can throw a lot of processors at it. Anyway, I'm going to use the largest one. Over here, there's also an option to do adaptivity on the surface, on mesh, and that is pretty handy. So if you click adapt mesh size, what it's going to do is it's going to make the mesh finer right here where there's this shape. And so what that's going to do is better resolve it. So we'll select that. Well, actually, I'll show you what it looks like without it first. So here's the mesh that we got just using the default settings. And you can see these big elements, you know, they resolve it pretty well, but they kind of miss the corner a little bit. So if I delete mesh, and then I come over here and now I add adapt mesh size and I mesh it. It doesn't take too much longer because it's not adding that many more elements. But it's going to do a much better job. See? So now your surface is much better resolved. So once you've done this, now you can go ahead and add your boundary conditions. And you'll notice by default, it assigns a block to the mesh. So these other blocks, so block 4 was the one we just done, and these were the 2 that came in with the TET mesh. So I'll just delete those.
So Kurtis, just to pause before you go on, there's a question that came in. You may have already addressed most of this, but the question was, what is wrong with the initial TET mesh? What was the motivation to obtain your hex mesh? For example, you might just use a TET 10 to get rid of locking.
Okay, so you can use, so I said this in passing, it's an entire conversation. So TET meshes, there is technology that allows you to use TET meshes on a plastic problem like this, because we're going to use a viscoplastic material model for the metal. And there are technologies like the composite TET that you can use. There's some trade-offs to them, but in this particular case, what I was showing in the beginning is the quality of the TET element was so low that those TETs would invert. So what you could do if you really wanted to use a TET is you could delete your CDFEM mesh, and then you could make a new TET mesh from scratch. There are some people that are trying to smooth the CDFEM meshes, but I haven't seen a mesh generated by CDFEM that is smoothed well enough that I would use a TET mesh. And in my experience, I still find that I get better. If I can get a high quality hex mesh, I prefer doing that because some of the stress averaging that goes into those other TET technologies can create a soft mode that is not a big deal in most cases, but in a case like additive, when it gets really hot, it can create some issues, some instabilities. So I think those will eventually be handled, but for now I use the hex mesh. So does that answer that question?
Thank you. Yeah, if there's a further question, I'll ask you.
All right, go ahead right now.
No, if I'll wait for that person to respond. Then if
oh, I see the Q&A thing here. I wonder why I can't actually see the questions.
Yeah.
Anyway, yeah, so I guess in theory, you could use TET meshes in certain cases, and there's trade-offs, which is a whole different discussion. But the CDFEM, that cutting technique, it just makes them such a poor quality, you really cannot use them. So that's why you want to use these hexes for now. So anyway, So now I have a block, but notice the thing that's unique about Sculpt is the mesh is disassociated with the CAD. So all the other meshing tools that I've used in Cubit, the mesh is directly associated with the CAD, which is really handy for selecting boundary conditions and whatnot. But Sculpt, the way it works, you don't get that. So when you select your node sets, what you're going to have to do, or your side sets, is you're going to have to select nodes inside the mesh. So for example, if I want to make a node set 11, I'm going to have to select it based on Cartesian coordinates. So you can use this node with y coordinate less than 0. And that will select it. And typically when I do something like this where I'm using Cartesian coordinates, I'll do this first. I'll say hi, node with y coordinate less than 0. And you see it highlights them. So now I know what node set it's selecting. And then down here, I can just node set 11, add node with y coordinate less than 0. So it created node set 11. Again, I could have used this GUI, which it will look, oops, I was using it wrong. Anyway, but I don't, for adding boundary conditions, I don't typically use the GUI because I can just type that. And now if you draw node set 11, you can see there it is. So you can, it takes a minute. I won't do it in this demo, but you can use that to construct all your boundary conditions. And so another important step is draw node set 11 and draw block all. Oops. You want to draw your node sets and your blocks just to make sure that everything is in a block and a node set, so you don't have trouble there.
So Curtis, Trevor asks if isn't there an option in Sculpt to create side sets on mesh generation?
Yeah, there is. I just don't know. I just don't use it. But yeah, there is. In fact, I don't know why this isn't coming down. I think by default, it actually runs. I can't remember. But yeah, there is, but I didn't use it.
Fair enough.
Let's see. So those are the kinds of things like, the truth is on Cubit, I've learned how to do a handful of things and I keep redoing it. They're always adding new features. And that's why I think it's important when you do stuff to talk to developers, because there are different ways to do it. So yes, Trevor, you're right, but I'm not doing it that way.
As far as talking to developers go, obviously, there's the connection with Sandia, but also we have a new discourse form at coreform.com. And so that's another forum where anyone's welcome to interact with developers as well.
Yeah. So a lot of times those automated tools like Trevor's referring to, they don't quite do what you want. So that's why I like to do things more manually, like I just showed, to have a little bit of control over it. A lot of times they work pretty well, but sometimes not quite what you want. So I'll export the mesh. We'll call it hex mesh 1, yes. And now we're done. We've made a sculpt mesh of one iteration of CDFEM. So if you go over here, you can see, well, Cubit will generate a command history. So we can come over here. There's two ways to do it. You can copy and paste it right here, or you'll find that there is, I have mine right here. It generates these Cubit.1. That is a command history, or there's this one, which is done in Python. And so all this you can do in Python. I'm not doing it that way today, but that's another option that's pretty handy. So I just copied and pasted from here because that is what I most commonly do. You can paste it, there's a text editor right here native to Cubit, but I don't typically use that because I prefer being able to use VI. So we'll call this so then we can paste it in there, and then you can go through and delete some of the commands that maybe you don't want anymore, like vertex visibility isn't going to matter much. we don't need to preview anything. We won't web cut it. Okay. So here now you have a journal command. And so you go through and, delete some of these things that you don't need. Like probably we don't need to draw the quality of the mesh when we're automating it. So now you have this journal file that you can run from Cubit. So there's two ways to do that. You can use this play button here and just grab it and then it will rerun it. Or you can come down here. Sorry, my pictures keep getting in the way. You can come down here and just type play and then give the path. And typically what I'll do when I'm doing something complex that has a lot of steps is I'll copy and paste commands as I find the ones I want. And then I'll just sit and play that same journal file over and over here. So we reset it. Typing reset just resets everything. Now I can play that journal file we just made. You'll see it'll do the exact same thing. And again, it will take a minute just like it did last time, but it will do exactly the thing. Now, in this case, remember the trick is we have many different geometries we need to mesh because we have different iterations of that CDFEM, all those different morphologies. So we really want to be able to run this on all those. And you couldn't do that in the GUI like this. It would take too long because there's hundreds of them. So in our case, if you navigate over to the TEP mesh, you can see that I have I have 9 in here. Sorry that this is in the way. So we want to run it on all of these. So there's a couple of ways to do that. Like I mentioned earlier, I would maybe write a bash script and then you use a stream editor like awk or sed. And when I say sed, it's SED. And what that would do is you could use those to just change text inside of here. So you would change here at the end of this command right here, it's telling you which TEP mesh it's reading in. I would just change the number since that's what's unique about each of those using sed or awk. Another thing you can do is templating tools. I use Jinja, which is a Python library, and that's very powerful. And that's handy if you're doing other things like I was in this model where you want to, Cubit isn't the only thing that you're dealing with. Jinja is really nice because you can template everything you're doing. But you can also just do it inside of Cubit, and that's what I'll show you how to do. So if you go to Cubit's help, where is Cubit's help? So if you go to Cubit help, you can search loop, and you'll find this tool called Apri Pro. And if you click on it, you'll have all of these marvelous examples of things you can do with Apri Pro. And I highly recommend you look through these because Apri Pro is very powerful. It's essentially like this internal templating tool that can do math. So it's really great. So I copy and paste this example, and almost everything in Apri Pro is self-explanatory, right? So here you have a loop. It does it 10 times, x equals 1. You add 1 here. We're not going to do any if statements in ours. So I'll just take the top part of the loop and put it at the beginning of this journal file we made. And then I'll end the loop at the end of it, and I'll leave the x plus 1. Instead of x, I'll use a because that is the thing I use. And instead of doing it 10 times, I would do it, I'm going to do it, we'll say 3 times. Oops, I opened a new terminal. Sorry about that. Now, what Apri Pro does, like I said, it's templating. So A, anywhere you put a curly bracket A, it's going to replace A with whatever it's equal to. So the first iteration, A is equal to 1. So if I come over here to the end of this, and I replace this 9 with a curly bracket, oops, A, then when I run this, what I'm actually going to get is 0, 2, 3, 1, because it will put in 1 instead of A. And then when it gets to the end of this loop, it will add 1. And so the next time I come around, A will be a 2. Does it make sense? So this is really nice because in those TEP meshes, they're numbered chronologically. So I can go 231, 232, and so forth. So I'll label our hex mesh as such. Now I can play that in Cubit. So you can see here, when I reran that journal file a second ago, it remade the exact same mesh. And you should always check your quality, which I just realized we didn't do. And you can see that these hexes are much higher quality than those TETs were. Anyway, so I can go ahead and rerun that journal file I just made. And now we'll have an APRE-Pro loop. So what it's going to do is it's going to run 3 times because we looped it 3 times. And each time it's going to pull in a different TEP mesh. And you can sit here and watch Cubit do its magic, which I find to be exceptionally satisfying, especially if you've automated drawing a CAD. It's very fun to just watch stuff get drawn. I mean, I really like it. So here, unfortunately, our TEP meshes are so big, it takes a second.
Can you answer a question while we're waiting, Kurtis?
Yeah, go ahead.
Okay. So this is from Emmanuel. I'm not sure if you already answered this. Is it possible to select the interface that I want to sculpt? For example, adapt the mesh size on the top, or the interface between the materials and no adaptivity on the bottom or inside?
Yeah, so I don't know if there's a way to indicate that by selecting the CAD. I would want to talk, I would want to ask a developer, but there is a way to add adaptivity, and I'll show you that in a second. And the way I do it is essentially you make a mesh. So the way Sculpt works is it has an overlay grid, and then it morphs that grid to fit the geometry. So what you can do is you can make a custom mesh and it will morph that to fit the geometry. And that is the way that I have incorporated adaptivity. And I'll show you that in a second.
So also just Trevor chimes in that he believes this is an enhancement request, the main part of Emmanuel's question. So
yeah, I wouldn't be surprised, but if that capability is there, I haven't used it yet, so it would be newer.
Great.
Anyway, so you can see that it's running, and each of these are different. We can't select them and see, but you will not, if you're running this on a compute cluster, you're not going to want to have a GUI opening up. So the way that you can do that is you can use some of these options. So when you open Cubit, there's all these options. And what I do in my bash RC file is I just keep a list of all the options so that I don't have to remember them. So these are the options I use. So the ones that we want to run it without opening the GUI would be -batch and -no graphics. And then -input will allow us to point to a journal file and run that directly. One other thing I'll mention now that I'm reminded of it, right here, you'll notice I have this -working directory, $PWD. So in my bash RC, the Cubit executable is aliased this way so that when I type Cubit in a terminal, it always opens up in the directory that I'm already in my terminal. This is super valuable. There's nothing more aggravating than opening Cubit and it guessing where it thinks it wants you to be, and it's not right. So if you do this, it will be the right directory that you're in your terminal. Anyway, so we'll type Cubit -batch -no graphics -input, and then we'll use that journal file that we made. And there you go. Cubit is open and it's running, and there's no GUI, but it's outputting, metrics so we can see that it's actually doing what it needs to do. So if there's any error messages, it will output it. So you'll notice that it is still generating history files and journal files. I can turn that off by doing -no information, but I didn't do that. Another thing you can do if you're using Unix is you can do a caret to a log file, or I think there's a log file option in Cubit as well, so you can have a log file, so that's pretty handy. So if we go into our TEP mesh directory where we've been saving these, you'll see there's our 3 hex meshes .g files. If we open those up, I like to view them in ParaView. You can see.
One more question while this is opening up, Kurtis.
Yeah.
Is it possible to implement the journal script in a Python script so that I could, for example, import a CAD model and some parameters, mesh the model, export the mesh, and then go back to the Python script to run the rest of it?
Yeah, that's what I do in Jinja. So I was tempted to come prepared with explaining how I do that kind of thing personally, but I thought maybe since this isn't a Python webinar, that maybe it would be a digression. But absolutely, that is absolutely something you can do, and I would encourage it. So most of the automation I do actually is in Python. Once I learned how to use Jinja, it changed my life because it's such a powerful templating tool. And I often will just do little steps in Cubit and export something and do something to it and then re-import it into Cubit and, kind of cut up my workflow that way. So pair view's ready. So we can see here's the mesh it made, and this was all automated. So let's open up another one just to show you that they're different, that it's using all of our TET meshes. Let's do that one. Although I think that's one I had pre-prepared. So you can see that one's slightly different. Notice the morphology has evolved because it's bulging out right there. So basically that's that laser moving away. So pretty cool. So I don't know, it's 10:45 now. I can show how I do the adaptivity, or we can just pause for a minute and talk. What would you like to do?
Yeah, let's just pause for a minute and see if there's any questions that come in. And then we can move on after we get a chance to address some questions. Here's another follow-up on the previous conversation about TET meshing, Kurtis from Anatoly.
Okay.
So his comment is, it sounds that the geometry respect is important in terms of accuracy in the considered problem. However, Sculpt is not accurate enough in terms of external geometry discretization if we compare it with Cubit TET mesh. So isn't it more logical to use TET mesh for this problem?
I don't know. So there's debate about, when you should use TET meshes versus hex meshes. The point I'm making is that, so for me, working in the environment I was working at the time, hex meshes were a better choice, just because hex meshes were more stable. And since I'm dealing with a high temperature material, I didn't want to have some of the problems that the TET meshes at that time were creating. But yeah, there's debate whether you should use a hex mesh or a TET mesh for any given case. But the point that I wanted to make is that the mesh generated for the fluid model will not work for the Lagrange. So you could, if you have a tool that will immerse a TET mesh, you could make a TET mesh on it. I don't know if Cubit right now has an equivalent of Sculpt that will do a TET mesh available. Do you know, Randy?
No, not an equivalent. No, it's
okay. So one of the issues is you'll notice the TET meshing tools in Cubit, they require you to cut up your CAD a little bit, but this CAD you can't cut for one. And you'll notice that the way that the shape is, you're not going to be able to mesh that easily with any tool other than Sculpt, because it's just not going to map and sweep or pave and sweep well. Does that make sense?
Great, thanks, Kurtis. Oh, and then Trevor just mentions that you can also convert the hex Sculpt mesh into TETs as well. Yeah, Kurtis, I would say, oh, here's one other question from Kenny. Does Cubit have an interface to generate a mesh from an implicit or level set geometry definition?
An interface? So you're asking if there's like a GUI that's automated this process?
I don't, I mean, maybe GUI just doesn't even have the capability.
Well, that's what I'm showing. So this mesh, this geometry was generated from a level set and a fluid model. That's what CDFEM does, is it tracks the level set. So I created a mesh-based geometry from that level set that was defined by CDFEM and then meshed it with hexes. I don't know, I may be misunderstanding the question a little bit.
Okay.
Does that answer the question?
We'll see if Kenny comes back and with any more questions. Okay, I would say, Curtis, go ahead and finish up that last thing you wanted to show then. And then any other questions can go ahead and come in. Oh, here's a last clarifying question from Kenny. Could you input an equation to define a geometry such as a TPMS?
Can you define CAD using mathematical equations in Cubit? Is that the question?
Perhaps.
Yes. What is TPMS? I think I don't know what you're referring to, Kenny. Is it possible to?
Okay, so Kenny is saying that it stands for triply periodic minimal structure like a gyroid.
Yeah, I think there are ways to do that. I'm a little reluctant to say because I haven't done it myself. So actually, I should say I don't know. I don't know if you can do that in Cubit or not. I think that would be a good thing to ask a Cubit developer. I would think there's a way, but I don't know for sure.
Yeah, you might want to ask that on our forum, forum.coreform.com. We got a lot of people looking at that who might know the answer better. I'm not sure either.
Yeah, I personally haven't done something like that.
Yeah. Here's another question from Chris. Is it possible to implement the journal script in a Python? Oh, I think we already answered that one. Yep. Yeah, we already talked about that, I think.
Yeah, and that's actually, Chris, that is the way I recommend working. So Python's very powerful.
Okay.
Is there anything else?
One thing I could add there, from the GUI, you can, we've added many hooks to Python. In other words, you can be in the GUI, adding even your own commands and command panels and Python scripts, launch them directly from the GUI and stay in that environment and still be working in Python. There's quite a bit of functionality to do that for what it's worth.
Thanks, Randy. Here's a question from Jorge. How would you handle more complex geometries? For example, adaptively refining multiple components, operations on multiple level set sign distance functions.
Okay, so to do something more complex using Sculpt, what I would do is I would make the custom grid like I was showing you. And this is a little bit harder. And it's why I recommend talking with Cubit developers. At least that's what I did. Because again, my expertise is in physics. I'm just using Cubit as a tool. But I'll show you how I did it. So what I have, let me go to Cubit here. So suppose that we want to make, so we don't have time to make it from scratch, but I have so I can run a journal file and make a mesh. So suppose I wanted to, oh no, I didn't make a journal file of it. So suppose that I wanted to have a mesh that looked like this. That I wanted to have some refinement in a certain spot. So for example, .g. So I made this before the webinar just to test it out, but see, I've cut a circle inside of this square and I want to sculpt that to my shape. So that's what I'm doing for this example to put adaptivity in there. But you could do something different. Like you could make your immersed, suppose that you wanted to do this model inside of something shaped like a house. You could cut a house and mesh it and then do sculpt in the middle of that and have a little spot in there where the mesh is shaped like that. And the way you do that is there are these two files you use. And again, I would highly recommend talking with the developers because they know more about this than me. But there is this Diatom file, and this basically tells you the STL file that you're going to mesh. Okay, so in this case, I would export one of those TET meshes, those TET-based, meshed-based geometries I generated from the TET mesh, and save it as an STL, and then I would put the file path here. And then I would run this input deck, and I would tell it the input mesh. So I've named it mother mesh, and that's the mesh I just showed you. And then I would tell it which Diatom file right here and name the output, and then it will sculpt inside of the mesh that I chose. And this is very powerful. This is how you're able to, more customize your sculpt. So the way you do that is -I, you do sculpt -I, and then your input deck, and then it makes the mesh. And the mesh, we won't wait for it because I've already made one. The mesh it makes looks like this. I don't want to ever see that again. So here you can see I have, I'll turn on the edges so you can see the mesh. So I have, this is the mesh I made, and then I sculpted the inside to it. So if I turn off the outside block, oops, I turned off the inside block. You can see inside of here, it's sculpted to that shape. Now this doesn't look great because I didn't make a mesh that would work well for that shape, but you can see it sculpted it to the inside. So I actually have two, here, let's take a cross section. So you can see I have these two meshes where sculpt, oh no, oh, I picked the wrong one. So you can see sculpt meshed, you know, it sculpted the STL into that mother mesh that I made. So this is the kind of stuff I would do to do those more complex cases. So on the example I showed you that we used in our paper, this one, what I did is I made this mesh here, which basically had refinement where there was a hot spot and a stress gradient, and then it was coarser on the outside. And then I ran sculpt, and this outside block right here, I just deleted it. And then I ended up with this mesh here. So you can see the hex is adding. And this was nice because, you know, then the material that was already there stayed consistent. So for example, in this example I showed you, you can see that the hex meshes even down here are kind of changing, and I would rather that not happen. I'd rather it stay the same here and only change where the morphology changes. So when I use that customization technique I just showed you, that's what happens. The mesh stays the same because I'm using the same mother mesh, and then it only changes where the morphology is added. So it's pretty handy. Does that answer that other question?
Thanks, Kurtis. Okay, well, we're coming up on, yep, Jorge says it does. Thank you very much. Here, we're coming up on close to the end of the hour. If there's any final questions, we can stick around for another minute or two. Others, I'll just like to express my appreciation to Kurtis. Kurtis, thanks again so much for coming and being willing to share your expertise with Cubit with us and preparing the webinar. And thanks everyone for coming. So again, if you have not been using Coreform Cubit, you're able to get a free trial at coreform.com. Also, there's Coreform Cubit Learn, which you can use for non-commercial use. And we've talked a lot about the community of Cubit developers, and one way to interface with those developers is at the forum.coreform.com. So thanks again. This webinar will be recorded, so if you have any, if you want to watch it again, it will be up on our website. And hope everyone has a great day.
And thanks for all the good questions. I enjoyed it.